All right, so the first issue right away, and some of you are probably screaming at me already because, hey, look at the noob and what he's doing. Well, okay, fine, fair enough. The first issue right here is our setting. We probably shouldn't be set to 10x, mostly because that will increase the... So it's kind of weird. So for example, if we're measuring 1 millivolt, technically speaking, the 10x here, or I should say 1 volt, pardon me, if we measured 10x here, the 10x actually puts in a voltage divider. So now, technically speaking, instead of our scale on our oscilloscope, for example, being 1 volt, well, we would have to multiply that by 10, so our scale would be 10 volts. So if we put a 1 volt signal through here, we would be, if we probe the 1 volt signal, we'd actually be looking at 1/10 of a division now, instead of full scale at, if it was set to 1x, which is, not that great. That means that there's a, there's a reduction of fidelity right there. Now, don't get me wrong, the 10x probes are excellent because they don't load your circuit. They reduce the loading on your circuit by increasing the impedance, input impedance of the probe, and that's fantastic. But in this particular case, we probably don't want that because we're looking at a very small signal. We don't want that huge divider because we're looking at a very small voltage, so of course that divider is going to obviously divide that voltage down so that we're even seeing less or even getting less signal than we would normally get. And the other thing is that the 10x probes are really good for a high bandwidth. They typically have a better bandwidth response at higher frequencies, but in this case we're interested first and foremost in a 4.8 kilohertz PWM signal, which is already fairly low frequency, but all of the components of that, because it is a square wave and there are higher harmonics and all that sort of junk that are generated by that square wave as you get that rising and falling edge coming up and down. But we're not interested in that. We're interested in if we have any feed through for the moment, and we're looking directly for that 4.8 kilohertz signal. It's possible there are going to be higher harmonics that come through, but at the moment we're not looking for that. If we see any of that signal coming through, we already know we have a problem, right? We're not worried necessarily about the 3 or 4 or 5 megahertz of the third or fourth or fifth harmonic. That's not an issue right now. We're worried specifically is that PWM, that 4.8 kilohertz PWM signal coming through and bleeding through, or feeding through, I should say, that RC filter. So, that being said, we should be using the 1x bandwidth, which will allow us to go down to get a lower, to take a reading of a lower voltage with a bit better fidelity. But of course, the trade-off is that we can't get as high a bandwidth. In this case, this particular probe, if I remember correctly, is DC to 8 megahertz at its it's 1x setting, but that's okay because we're not looking for anything anywhere near that end of that range. So that's our first problem. So now that we've fixed that, we're going to go scoot back to the scope over here. And of course, the first thing that's gone on is our signal has gone all over the place, but that's because we still have to go in and adjust the ratio. So now we'll adjust it for a 1x probe, and now we're set to 500 microvolts per division. That's a heck of a lot. So let's go bring this down to, in fact, actually, I'm going to shut off this light again so we can see what it looks like without the, okay, so this is not so bad. So these are with all the lights off. All right. So we're still looking like we're getting, 9 millivolts per peak to peak, and I'm going to go ahead and I'm going to shut off everything now. So everything's off. So this is our nominal noise floor at let's say 3 millivolts peak to peak. Okay, so this is with every single thing off. The device center test is off. The power supplies are off. Everything, or I should say, the outputs are off, not necessarily the power supplies. So let's go ahead and do the same measurements. So we're going to turn on the 644 Arduino, we'll turn on the output stage, and we're going to turn on the actual output. And now we'll do a measurement as soon as it comes in, comes down a little bit here. Anytime. Alrighty, so let's bring this into, alright, so now we were at 3 millivolts, now we're at between 9 and 8 millivolts per peak to peak, so that's pretty bad. that's not fantastic. Of course, actually, why don't we do this properly, because it's probably measuring the peaks of these high points here. So let's actually measure this via here. So it's about 2 millivolts per division right now is what we're measuring here, this noise here. And if I turn this off, it's going to fly around. And again, you know, it's not a heck of a lot. It's, you know, give or take, still about 2 millivolts per division. So that's still, you know, if there's a problem, it's possible that the noise floor of the setup that we have is still too high, and we're not picking up any actual noise induced on the outputs by, for example, any of the PWM. And in addition, if we look here, so technically speaking, here's the PWM waveform, and I'm not entirely convinced that these two peaks here are caused by this PWM, but there's one way to find out. And that way is, let's go and first of all turn our triggering to channel 1. Okay, so oops, channel 1. I hate this sometimes. Okay, so this is going to bounce around a little bit, but we're going to go and we're going to, all right, so, you know, okay, it's not perfect, it's not a great image, but it should be good enough to prove that if we turn off the PWM signals, we should see these disappear. So let's try and do that now. We'll turn off the PWM. Aha. And they're still there. So it means these are not being generated. And in fact, we'll turn that off too. Ah, okay. So those two signals were generated not by the output stage, but by the 644 Arduino itself. So we were getting feed through, or I should say, we're picking up somewhere that PWM. Now, again, I am not convinced it's necessarily the setup. We'll have to see, but here, let's go turn that back on for a second. And you see now when I disconnected, and I'm going to show you what I just did. Zoom that out. Pardon the darkness, I just don't want to include. So I actually just removed the probe, and you can see now, without the probe in there, everything's fairly clean. So we're definitely getting some feed through, but not necessarily directly from the MOSFET. I'm not entirely sure that's the case. We'll have to see. That's something we'll have to check. But the first thing right away that I would say we have a problem is because if we take this probe out here, we go down to, you know, bugger all, sweet bugger all. If we go to, you know, okay, so it's, whoops, wrong one. That's like, I don't know, 400 microvolts per division if we have the probe completely disconnected here. Well, of course, we're picking up some of the waveform, but if we move it away from everything so that we can't get anything, and okay, so we're getting about 500 microvolts per division. That's not per division, peak to peak. So, how to get rid of that? Well, we have another tool in our arsenal we can use. Alright, welcome back. When you absolutely, positively do not want to fuck around, one of the best scopes to go to is one with a darn low noise floor. Now, the 2225 by Tektronix, which is a 50 megahertz dual trace. Sorry, not dual trace, probably single trace, but no, yeah, I think it's called dual trace. Anyway, I don't remember. There's one where there's actually two guns, and there's one where you have a single gun firing, drawing both traces, and that's this case. This is a single gun in the back, electron gun drawing both traces. So anyway, I think it's called dual trace. Anyway, when you absolutely positively don't want to fuck around, you use one of these guys. This one has a 500 microvolts per division setting, which is the same as the Rigol we were just looking at. However, this one I think is a little bit cleaner, and we could try and do, for example, we can switch to the high resolution mode in the Rigol, which may get rid of or may clean up that signal a little bit. But you're throwing away a lot of data doing that, and I'm not convinced that it's giving me as good a reading as I would like. So I'm going to switch to this. There are people that may say, "Hey, DSOs are just fine," yada yada yada. It's possible. I don't know, so I'm going to try it on this, and we'll see. So we just keep in mind we got 2 millivolts peak to peak for our noise measurement. It's the best we could do, quote unquote, on the Rigol. Let's see if this one's any different. Now again, the setup's identical. The bottom trace here, which is channel 2, is our PWM signal, or the top trace is channel 1, and this will be monitoring the noise from the output of our power supply. same setup. I might adjust the sweep speed a little bit. I'm going to bring out and bring up the intensity a bit. So now the top trace here is 500 microvolts per division. And you can see, so it's basically the noise here right now so far with everything off. The noise is basically 500 microvolts. So we're going to go ahead and we're going to go turn on some stuff. So that's the 644 Arduino. I'm going to turn the output on here, and we're going to bring this up as high intensity as we can. So far, okay, so we can see here's our pulse here. We got some crap in here that we can see, but it's not too bad. Maybe it'll be easier to see if I turn that down a bit. But anyway, yeah. So there's some stuff that I can barely see on the screen here. So we're going to go turn the power supply on and see what happens. Aha, there we go. Now, we have a little bit of extra, but now, okay, so this means, and again, let's crank that up a little bit. So we're seeing, again, we're seeing maybe 1.5, so maybe 1.5 millivolts, something like that. So to me, this is saying that, okay, our noise floor is much lower on this setup, and with the power supply on, there's not a lot of noise getting through to the output. I mean, there's still a little bit, but we're talking maybe, you know, maybe a couple hundred microvolts or something like that that's getting out there. And sorry, actually, pardon me, it's less than 1 millivolt, pardon me, it's 750 microvolts, say peak to peak. So this seems to be showing that the actual noise it's feeding through, and of course there's no obvious thing going on right here where you'd expect something that's feeding through from the PWM to, you'd expect some sort of weird excursions here, some weird signals on both the rising or the falling edge here of each of these PWM pulses. And there's nothing. So this to me is showing me, well, okay, I think we're all right. We're not seeing any major feed through. And then of course there is some of it here, a little bit. And that may be, again, because we have some weird stuff going on with the setup we have here, some either not inducted, but some not conducted, pardon me, but some sort of emissions that are going on that are coming off the board. So maybe we need to isolate or shield the part that's converting the PWM to a voltage. So we'll have to see. But we're going to go ahead and turn on the electronic load now, and we'll see what happens. All right. So now we're pulling about 360 milliamps. I'll bring that down to about 300 milliamps. And already you can see, wow, look at this. What's going on here? We've got this huge waveform. Of course, huge. Don't forget, these are still 500 microvolts per division. So, you know, let's look at this. We're going to say 1. So it's 1, 2, 3, 4, 5. So 5 times 500 microvolts. That's 2.5 millivolts peak to peak, roughly. And that's basically, you know, somewhere in the ballpark of 2 millivolts of noise, actual noise. But I feel more confident now saying that there's 2 millivolts of noise because I can see with the output, or I should say with the load off, I can see that our noise floor is showing us a lot less. So we're actually measuring something versus just seeing a lot of noise and not knowing really whether that's noise from our environment and setup or is there noise from the actual device under test. And that's all. It turns out that this particular setup is particularly bad when it's under load. But again, I'm not entirely sure now whether or not, and this is another set of measurements I have to do. Now, is this being caused by my circuit PWM / controlling the voltage and maybe not reacting fast enough or something like that to regulate it? I'm not sure. Or is there something in the actual supply, the actual power supply, that's making it such that when we put it under load, we get noise coming out like that? And I'm not sure. We'll have to see. And there's one other thing that's interesting. Let's go do that measurement really quickly. There's one other piece of equipment which we haven't really examined, and I think it makes sense to take a look at it quickly before we sign off for tonight. And that is our electronic load itself. Is this guy adding any noise to our setup? And this is, of course, the question I want to ask. Now, the easiest way to do this, of course, this is really convenient. It's nice to have an electronic load. You can just sort of dial in any current, and this one can act as either a constant current or a constant resistance. It's kind of nice. It's a nice thing to have. However, internally, the way that it's built is it's probably using some sort of control feedback mechanism now, electronic or electrical feedback mechanism, and that might be inducing pulses in the or surges in the on the supply as it's adjusting to maintain a constant current. And if it does that, well, maybe that is causing our voltage to fluctuate and inducing noise into the power supply. So what's the easiest way to take care of that problem? Well, all right, so why don't we go look here. So we have our output, we have our banana to BNC, and then we of course have our two electronic load lines coming out of here. So what we're going to do is we're going to just simply unplug those, pull that off for a second, open this up, and we're going to use a good old big fat resistor. And this one is a 330 ohm 10 watt. I haven't done the calculations. I'm pretty sure it'll be fine. Worst case, I blow up a power resistor and I'm not going to cry too much. So we'll put this right here. Oops, almost missed that. I think we're talking something like 12 volts or something like that with at about 300 milliamps, sorry. So it's probably in the order of about 3 amps. So it's dissipating a lot more than it's supposed to. It's probably about 30 watts or something like that if I have the math right on that, or is that completely wrong? No, sorry, it's a tenth of that, so it's about 3 watts. So it's probably okay. So let's leave we'll leave that like that. Of course, we'll plug back our probe back in now so that we can still measure what's going on with this thing. And we'll use this setup instead to test the noise. All right, back at the scope. And again, we can see our measurement we're making at the outputs of the power supply. Here's our PWM's output. I am going to, everything's turned on, so I'm going to go turn the supply on right now. Aha, all right. So now we can see very clearly, well, maybe a bit more jiggly than clearly, we still have our 4 divisions, or about our 2 point something millivolts, millivolts of noise, peak to peak. So clearly our output was not, or I should say our electronic load was not creating any problems for us, or maybe a little bit, but not enough to, an order of magnitude less than what we're seeing, maybe a couple hundred microvolts, but not 2 millivolts worth. So this just again proves or removes one piece of test equipment from the equation that could be possibly causing the issue. So it's not the electronic load, maybe it's the power supply, so I could probably try a different power supply. I have 2 of these 650As. I could try and see if they both have a similar behavior. Of course, the output of that PWM is definitely leaking through. As we saw, we have these little bit, let's bring that up. Actually, I'm going to turn off the bottom trace. Oops. And I'm going to bring that up. You can see, oh, maybe you can't. Anyway, that might be a little difficult to see, but you can see these little peaks right here. So those seem to be caused by the Arduino. If we shut all this off, we should see all of that just magically disappear. So what's the next step here? Well, if I really cared about fixing this, the next step would be to go clearly look at that filter, because clearly there's other components, other wave components that are either not being filtered properly or there's not filtered heavily enough. In conversation with a couple of people on the EvaBlog IRC channel, I was getting the impression that it was very difficult to do this properly, and they're probably right. So I might choose a completely different mechanism for generating my reference voltage to control my voltage-controlled resistor in that circuit. So we'll have to stay tuned for a different video on that. That's a whole other topic. So just keep in mind when you're doing measurements like this, and again, I'm discovering all this at the same time, but I kind of knew a bit about what was going on, and it was worthwhile picking a bit further at all the problems. And it's the same thing when you're doing any experiment. Look at what you're doing, ask yourself what you're measuring, ask yourself what your possible sources of error are. Where could you be making a mistake? Where could your equipment be lying to you? Where could your test setup be causing you issues? All of these things are very important to ask anytime you do any kind of experiments or anytime you do any kind of measurements. So have fun, get out there, build stuff. Remember to be careful when you're doing your measurements, that you're measuring what you think you're measuring, and not assuming what you think you're measuring wrong, if that made any sense. And I'll catch you next time. Cheers.